We're able to make design decisions in simulation. You can say, okay, is this going to be what works well? So for example, we were able to test out different turret gear ratios on our turret in our simulations, and we were able to find the optimum value, which is not actually a very standard number. It's not a 2-to-1 or a 1-to-1 or a 3-to-1. It's actually somewhere between a 2 and a 3-to-1. And the second one is the reason is that we can get, because of this, we're able to get the robots and also specifications to the electrical and software team sooner, because we know the exact characteristics of the robot, and because we're faster at prototyping, we can get them a physical version sooner. The final reason is that we can optimize our system performance. So, like I mentioned with the gear ratio, we can choose that. We can also make design decisions at the beginning of the process for which kind of motor we want to use, as well as other things.
There we go.
So for the first simulation we used is for FEA, and this is pretty standard. A lot of teams use FEA. So we did this for a suspension, and this year we did this for a suspension and also for our box tube and our chassis to save weight. So our standard is 15.5 kilos, which is a lot lighter than a lot of the teams here. However, we still have full capability, full suspension, and a full halo to protect the arbor panels. And for suspension, what we did is we picked a spring constant and damping and geometry to optimize going over the bumps. So we knew that these bumps are going to be not that big of a step, but we want to be really smooth going over them. A lot of teams saw the video of our hero, which they're like, there's no way that thing's going to be stable. But when it was going over the bumps, that hero did not wobble like nearly at all, and that's because of our simulations. The other kind of simulations we ran was on our box tube on our chassis. So if I pick it up, you can see right here we have slot pockets right there. That was because of our FEA simulations. A lot of teams will drill holes, but because of the slot pocketing, we were able to optimize weight without removing much strength at all.
It removes no strength.
This removes pretty much no strength in our application. So for our dynamic applications, we really have two things that we spend most of our time on, our turrets and our drivetrains. We're only going to really be talking about our turrets, but our drivetrains probably warrants about a whole hour talk, as it took about 8 months to develop the entire simulation. But for a turret simulation, we designed the optimal controller, we picked the gear ratio, and we also were able to choose which motor to use. And for the drivetrains, we were able to limit power without a current sensor, avoid skew while spinning, and we were also able to, and we do this by maximizing angular velocity given a linear velocity. And here's some of our graphs of our saturation limits of our motor with our controller. And as you can see, we're pretty much in use. We can use almost the entire motor power. We do have a 10% dead zone that we will get to later.
Case study, turret controller design. So to design, let's say we want to design a turret and the turret controller, and we want to make it really good, like really good. First thing we did was first figure out the model for the turret. So we need to figure out we need to simulate and figure out all important dynamics and at least acknowledge everything that's less important. And for the simulation, then once we have that model, we need to actually build a simulation for that model. We want to simulate everything major and as many minor dynamics as possible. Everything you don't simulate can bite back at you and cause problems. But once we have a simulation, we can then use the simulation to design the controller, because you can see what's going on in the simulation significantly better than you can see on an actual physical robot. And then once we have everything in design and simulation, we can then apply it back to the design process to influence design decisions and then tune the robot. So model derivation. There are a bunch of phenomena that are relevant. So we have a motor, of course. The turret has inertia, wet and dry friction. But additionally, there's relative velocity to the chassis, pure time delay, discretization, and the multiple frames reference. All of these need to be accounted for and influence our design decisions. And then, because we can't know everything perfectly, we have to make a few assumptions to make it possible to model. So we're going to assume that the turret is relative to the inertial frame of reference. The motor control is a unit gain, because does anybody else know what C620 does? And then the transmission is rigid, because if it's not rigid, you have problems. So model derivation. The turret will experience wet and dry friction based on how it is moving relative to the chassis, not the inertial frame of reference, relative to the chassis. Oh, why are you doing that? And the turret will also experience inertia in multiple places, but we can just use a lumped parameter model and lump it all as a single inertance term. And then because it's moving relative to the chassis, you have to explicitly account for that in your friction terms. So we end up getting the mechanical side being mostly second order, with the dry friction making everything a little funny. Go. Now for the motor model. DJI gives spec sheets. However, they are not very good. They are inconsistent with each other. Okay, take that. So for example, the 3508 model parameters, you might remember seeing some physical constants. That's for trapezoidal motor control. They are not accurate for our usage. Instead, we had to actually interpret from one of the graphs they gave us that actually gave us the correct parameters shown here. But the 6020 parameters are accurate. Other modeling notes. Back EMF is due to relative motion to the chassis, not absolute motion in the inertial frame of reference. So you must account for that. And that the torque constant and back EMF constant are not quite equal, which means you have to use two different constants there. And then motor output has gear ratio between the motor and the physical system. There we go. And then with the model, we can then get these three equations. The first two are the equations we use to simulate and include the inductance term. But when actually designing the controller, inductance is too fast for you to do anything about with your 500 hertz controllers. So if we ignore that, we can actually get acceleration as a function of just all the states of the system, which we can all measure, which gives us one nice equation that's nice for actually designing controllers off of. Step 2, simulation design. We want to simulate everything we know of. In this case, we use Simulink because the school teaches it, but if you know something else, it should also work. What is very important is to simulate sensor lag, because that actually is one of the primary limiting factors of these turrets at very high speeds. The 8 milliseconds has given me more grief than about anything this year. So then, the controls to actually pose a problem. We want to eliminate overshoot, minimize travel time subject to the following constraints: the voltage saturation, the maximum current limit, pure time delay of the sensors, the discretization, and then the system dynamics. But this is a hard problem. This is a very hard problem, but we just made a simulation, so we can explore the design space and actually work on solving it quite quickly. Dividing into the controls problem. You can split the controls problem into two separate problems. Do what you're told. Oh, scroll down. Two problems. Do what you're told, and then given the current state, ask for something reasonable. And these two problems are completely separate. The solution for one does not influence the solution for another. So that also makes the problem much easier to solve. Controls design. Problem 1, which desired velocity. We know the system dynamics, so we can just invert it, and we get all the feed-forward terms right there. No silly tuning needed. But because the model is wrong, we still want to augment the feed-forwards with a PI controller. And simulation shows that with time delay, you can't tune the feedback too aggressively, because now your feedback and feed-forward will start fighting each other, which we also observed in practice and matched up with the simulation.
One final thing about the last slide is that the model is not necessarily wrong, it's just slightly inaccurate. But for the problem number 2, generating a reasonable input. So we must consider the phase plane of the system, and we can split this into two phases: acceleration and deceleration. So our deceleration profiles are much more aggressive than our acceleration profiles. This is because our acceleration is limited by voltage saturation of the motor, whereas when we send it maximum power, and it can only go so fast. Our deceleration is limited by current and bandwidth limitations. So that's just how much power we have available in control. So for example, this is one big advantage of the 3508s that we're going to get to, is that they have they can facilitate a lot more system bandwidth than the 6020 motors that we used to use. Acceleration. So high velocity means the turret's going fast, which is good. We want to maximize our velocity during acceleration. From earlier, we have this equation, but because we know all the coefficients, it's just basic algebra pretty much. We know the equation, we solve this, and we can determine how much we can actually accelerate in simulation. we do limit this to 90% of 90% of what a theoretical maximum, because we want to add a little bit of safety margin, and it leads to uncontrollability if we don't. Now for deceleration, since this is currently limited by the motor controllers at 20 amp max, we are able to do this a little more aggressively. But if we want to do constant deceleration, this requires infinite system bandwidth, which means infinite input power, which is bad. So we must implement, and to solve this problem, we used to use a PI controller for generating our velocity, but this just wasn't good enough. So we added this a two-state phase plane controller. So for decelerations, as it approaches the target point, it uses this ramping down profile. But once it hits a threshold, it approximates to a straight line, and this avoids this problem where we require infinite bandwidth. And this was able to solve our overshooting problems we had last year at RMNA. So from this, we're able to make our profile generator and our position controller, which solves the acceleration and deceleration curves given the last requested state. We used to use measured state, but this was also problematic due to the 8 milliseconds round trip problem that was mentioned prior due to delay in delay in reading the IMU and in the CAM protocol that DJI uses. And we find the minimum acceleration, and then we use that to request the right velocity. We then send this value to our velocity controller. Now to actually apply this controller, we use a process, we call it SysID. So this stands short for system identification. It's how we actually characterize our real system because things aren't perfect. The way we do this is different between our chassis and our drivetrains. But for our chassis, we use a more complicated procedure, but for our turrets, our chassis and our turrets. But for our turrets, we actually use the white noise method. So we send white noise to our motor for about 100 or 200 seconds. And from this, we're able to, when we record this data using a J-Link, we then use this to determine the frequency response of the system. This gets us pretty close, but we also use this to identify the pure time delay. And there's a little bit of a shift, and at low frequencies, we should see no static gain, but we do. And so from this, we're able to characterize our dry friction of the system because nothing has zero friction. And we can compare this to the simulation to do so. Now, for our controller tuning, we do this all because we have developed the simulator and also our controller in MATLAB and Simulink. We're able to tune off the robot entirely. So we run our we continue to run our simulation with different constants, and by doing this, we're able to really dial it in to minimize overshoot but also minimize settling time. But this isn't quite perfect. So when we take these constants and put them over to the robot, they're going to be really close, but they're not going to be perfect. For example, on our Hero this year, y'all have seen it. It is very tall, and it has a very large hopper. And so our system dynamics were very different depending on the amount of balls in the hopper. And so when we started measuring with the amount of balls we actually were carrying, we had to retune the controller to handle the added inertia of the extra balls. Now, going back to the robot design process and kind of where this whole simulation-driven design process kind of ties everything back together. And this is why we chose a single 3508 motor for all of our turrets. This is because, as I mentioned, the 6020 motors, the hub mount motors that most teams use just aren't weak. Fun fact, the motors you are probably using for your index are over 2 times as powerful. They're just not, 6020s just aren't that good. And this over halves our 0 to 170 step time, which is also kind of the amount of time to turn around and shoot at someone behind you. And this capability also allows flick shots, which our driver Ethan was able to do in game, and also CV, which our Sentry was able to do and from other people found pretty terrifying. We need to work on our CV to make it a little better and not just dump 20 hertz for half the match, but that's a next year problem. So the other thing we kind of had to design in is we had to extrapolate for latency because it sucks. It really is the bottleneck we're having to deal with right now. And so as I said, we have our state estimator built into the system to solve this problem using our last known positions. And with our system parameters, we're able to take a pretty good guess, and this helps a lot. It's not perfect, but it's the best we can do for now. And our results from this is that we have the fastest turrets in RMNA. We have measured our times. We've compared them to CU. They are about the same, even though we are running half the motor. And we're able to have zero change in behavior despite how fast we spin. One thing that some teams have talked about is how when they're spinning at maximum speed, they're unable to use their turret becomes less accurate. We do not see this phenomenon. Our turrets behave exactly the same even when our robot is spinning at up to 12 radians a second. And pretty much, this is kind of overall a process for our turret, for our turret applications of our simulation-driven design process. And that's all. Does anyone have any questions? Uh, I guess it's a little silly, but
We put up blocks and we tell the motors to step through the range of currents, and based on that, we can figure out how much friction there is in the grease in the motors. And that's how we also discover that the grease difference is real. Uh, the wheel friction, most of the friction is from the gearboxes, and that doesn't change when it's on the ground. Like, sure, there might be some funny business with the wheels, but that's not significant relative to the friction in the gearboxes. For the drivetrain, we can just measure it in CAD. For the turret, you can run the SysID, and that actually gives you your inertia.
for the turret SysID, we just basically we don't run that while the robot's moving, and so we just hold a cable basically on top of the robot, and we let it just do its thing for a very long period of time. And I don't know if many of you use J-Links. We can't use an ST-Link because it just doesn't give us the live data logging. But through the J-Link, we're able to get data at like at our control loop frequency the longer we get the data, the better it tends to be because the more data, the longer it is, the better it is. But it's not quite as simple as that. There can be other factors, but yeah.
You need the robot to actually SysID it. But the other things that usually trend the robot is there might be like some quirky latency behavior. Like something like you might have like 3,000 work in simulation. Like you might be able to push unlimited, very high aggressiveness in the simulation. In practice, because like maybe the C620 has a slew rate we can't measure, you have to detune it slightly. It ends up being that after you run the SysID, you get everything you need, and the things you're tuning after the robot are just tuning down some high level safety parameters.
Next 3v3 match, but after the closing ceremony, we're gonna come back and do more of this. So, yeah, the next person.